Hi everyone, my name is Ruisi Zhang, a fourth-year PhD student from UC San Diego, and I'm really excited to present our work, Remark-LLM, a robust and efficient watermarking framework for generative large language models. And this is a joint work with my colleague Shehzeen, Paarth, and my advisor, Professor Farinaz Koushanfar. I do believe in the past 1 year or two, the most frequent phrases we have ever heard is large language models, which has truly transformed every aspect of our society, including healthcare, software development, content generation, and even more. However, with the wide application of such powerful tools, new security problems also arises, like how we can better use these generative AIs more safely and more traceable. The White House has recently published an executive order for regulating generative AI, and among those proposed approaches, watermarking as a way to embed information onto the AI-generated contents provides a promising way to authenticate and detect LLM-generated outputs, and has been highlighted in the order. So here is a global flow of how watermarking is typically being applied in those large language model applications, which consists of two modules, where in the watermarking insertion, after the LLM generated the contents, those information first go through the watermark insertion module to embed LLM owner's signatures. And then the watermarked content is distributed to local users. And another part is the watermark extraction, where LLM owners claim their ownership by decoding the signatures from the watermarked content. And then they compare the decoded signatures with their encoded ones for ownership proof and justify if the content has been generated by specific large language model. So watermarking texts has been significantly more challenging compared to other modalities, for example, images or audios. There are quite a few reasons. So first of all is the texts are more sparse compared with other modalities. For example, LLM-generated texts usually have a few thousand tokens, whereas a single image of 256 pixels has around 65K potential pixels for watermarking insertion. Therefore, there are fewer potential positions to encode the signatures. And also, the texts are more sensitive to smaller changes compared to images. For example, very minor token replacements in texts can distort its meanings and fluency, whereas such smaller changes in images are often more imperceptible. Besides, watermark texts are also more vulnerable to detection and removal attacks. So here is an overview of our proposed Remark-LLM. In the watermark insertion phase, the backbone sequence-to-sequence model takes the original LLM-generated texts and signatures as input, and it produces the watermark text distribution. And one of our contribution is that to ensure the readability of the watermark texts and enlarging the watermarking capacity, we employ a pre-trained T5 model as the sequence-to-sequence model's backbone. And by leveraging the model pre-trained on large text crops, the watermarking framework has a wider search space for potential tokens to replace as the watermark texts. And another watermark extraction module uses a transformer-based extractor to decode the watermarked signatures from the watermark distribution, and as well as the malicious transform text for robust message recovery. Here we randomly delete, add, and replace tokens in the watermark distribution to mimic the malicious transformation can happen in the real world after the local users receive those watermark texts. The watermark insertion module and extraction modules are being trained end-to-end with the aim to minimize the following losses. The first one is semantic loss, where we aim the input and watermarked content to be semantically similar. Therefore, we minimize the cross-entropy loss between the input texts and watermark distributions. And the second one is the message recovery loss, where we hope to ensure that messages are being successfully recovered. Therefore, it consists of two parts. The first part is minimizing the L1 loss between the input and the decoded messages from the watermark distributions. And the second part is minimizing the L1 loss from the input message and the malicious transformed text decoded messages. So with those trained modules, we can leveraging the watermark insertion model to encode message. The watermark insertion module leverages an optimized beam search to decode readable texts from watermark distribution as T plus M. By adding a small percentage of dumbbell softmax to the watermark distribution, we can get more diversified decoded texts and choose the one with highest watermark extraction rates for outputs as the watermark texts. As for the watermark extraction module, the messages are being decoded from the watermark extraction module. The encoded message M and decoded message M prime are being compared to calculate the watermark strength Z-score, and the LLM owner can determine if the texts are generated from the specific large language model or not. Then we evaluate the performance of the watermarking framework from the following aspects. The first one is BERT score, which measures the semantic preservation between the original and watermark texts. And the blue for coherence between original and watermark texts. And the WER as the percentage of decoded messages successfully matching the encoded ones. And we also compare with several state-of-the-art watermarking framework, where KGW and XP are inference-based watermarking, and AWT is neural-based watermarking, and K3 is rule-based watermarking. So here, compared with those baselines, Remark-LLM demonstrates, first of all, high watermark extraction rates, where over 95% watermark bits are extracted when decoding 64-bit signatures from 640 token texts. And also high semantic preservation, where it has 0.9 BERT score compared between the watermark and the original texts. And very notably, Remark-LLM also demonstrates very high transferability. That means once it is trained on the HC3 datasets, the rest of the 3 new datasets can be successfully watermarked without additional fine-tuning. And we also evaluate its watermarking strength. That is how confident an LLM owner can claim if the content is machine-generated or not. And by using the previously defined Z-score to calculate the watermark strengths, we found previous work showcased very sensitive trade-offs between the semantic preservation as well as the watermarking strengths, whereas Remark-LLM possess good qualities along both dimensions. And it also showcased its transferability and agnostic to text generated by different large language model architectures or prompt sources. And again, with the model trained on the HC3 dataset, we watermark texts generated by OPT, OpenORCA, and the Llama model. They are prompted with 2K instructions, prompts from Alpaca dataset. And the results also demonstrate similar level of watermark extraction rates, as well as semantic preservations and the coherence preservations. Here are more watermarked examples from our framework, where we can see the changes are being highlighted in yellow. And we found Remark-LLM not only learns to replace words with their synonyms, but also replaces the contents with words of similar meanings, and also learns to add the contents like deleting words to ensure an overall coherence. And as for the attack evaluations, we first evaluate Remark-LLM's robustness under watermark detection attacks, where the adversaries tries to detect if the texts are being watermarked or not. There are basically 2 approaches we are verifying. The first one is analyzing their token distributions, and the second one is using machine learning-based classifiers to detect if the texts are watermarked or not. Here we can find the word distribution from the original text versus watermark text are quite close. And the ML-based models also cannot confidently tell if the texts are being watermarked or not. Therefore, Remark-LLM is robust under the detection attacks. And we also analyze Remark-LLM's robustness under watermark removal attacks, which includes text edits, rephrase, and re-watermarking attacks. And we can see compared to the baselines, Remark-LLM maintains high ownership-proof AUC. And we need to note all of these is achieved while preserving the watermark content's semantic fidelities. So in conclusion, we introduced Remark-LLM, which is a watermarking framework that has high capacity, high transferability, and also robustness. And we also perform comprehensive evaluations on various LLM-generated and human-written benchmarks, which demonstrates the effectiveness of this proposed framework. And here is also our code and papers. Thanks for your listening.